Okay, that means section 4.5 is about the average cost. That means average cost is the cost per unit of producing a certain quantity, of course. And how can we compute? We can take the total cost, we can see this, the total cost, and divide simply by the corresponding number of produced units. And the average cost represents the slope of the secant line between the origin and that quantity, yes? That point, Q, CQ. Okay, you can see that's just the average rate of change, I can say this way. Okay? Now we can also try to find a minimum average cost, and this will happen where line is a tangent. We will have to find a tangent line to the cost curve. Okay? That means trying to find a tangent line, and that point, that quantity will give me a minimum, okay? Minimum average cost. So let's see. And this is some relation between the average and the marginal cost. And we can try to solve a first question, because we have to know how to apply, how to use that information. Okay, the figure below show a cost curve, CQ, in dollars for production of Q units of a product. Use the graph to estimate the average cost when the production level is 600 units. Represents the answer graphically. Okay, that's what we have to do. We have to find 600, I believe is here, 600, and I think the corresponding value will be helpful. Okay, that means what we need, the average cost, I can say this way, the average cost is defined as a ratio of the total cost divided by this quantity. And everything must be computed at 600 for 600 units. That means the cost at 600, laptop is too far away, and divide by 600. And what we have, the cost at 600, of course, 600 units, of course, is 40,000 divided by 600. Okay? That means this will be, that's by definition, that's the average cost when the production level is 600 units. Let's try to simplify. I can divide by 100, then I have 400 over 6. I can say 200 over 3, and 200 divided by 3. Now, of course, we do have a calculators during the midterms and the final. We don't have a calculator, we can leave it like that, but we know that 200 divided by 3 is like 6.6. 6.6. That we can say that the average cost is like 66.7 dollars per unit produced. Okay, that means that's the final answer, and I can say the average cost is just $66.7 per unit produced. Okay, that's mean what we have to know. I can highlight on this slide. Make sure that you know how to estimate the average cost. I should blue this, and that's the formula. Okay, that's mean make sure that we know is simply the total cost divided by the number of units. Okay, that's mean that's how we can compute this average cost. Okay, one concept done. Now let's look at the next one. Probably similar things. A company has a cost function, and we do have a nice polynomial, the third degree, okay, 0.01 q cubed minus half q squared plus 20q plus 1,000. That means this is the cost function in dollars. And q is the number of items produced. If 100 items are produced, find the average cost per case. This is exactly the same question like question number 1. The only difference is, instead of the graph, we do have a formula. And probably we have, the formula is not friendly. We have to use the calculator, but yeah, let's see. Let's see what we can do. Again, the average cost is simply defined as the average cost for the Q units, total cost at that Q over Q. Make sure you will probably remember because I'm typing, and we have to use 100. Okay, I can put this. And the only thing that I have to do, maybe I can write the short. I have to substitute 100 to the formula of the function and divide by 100. And as we can see, it's nothing. If we know the concept, if we know the idea, it's nothing complicated. Okay, I will just write this down for you. That means we can see I'm taking Q and substituting 100. And then 0.5, Q substituting 100. Oh, that's actually squared. And then 20, substituting 100, and plus 1,000. Of course, you can use the calculator for this because we want you to practice a concept. And I can tell you, I did this before. I mean, we can even try, right? This is 100 to the power of 3. We will have 6, like 6 zeros, right? 100 times 100 times 100, and multiply by 0.01, we have 10,000. And then this one will be 4 zeros times 0.5 is 5,000. Yeah, I'm always operating by zeros. This is simply 2,000 and plus 1,000. Wow, actually, we don't even need a calculator. What we have? 10 minus 5, 5 plus 1 plus 2, 8. 8,000, no, 80,000. Divide by, am I right? Divide by 100. Or maybe I am, this is 5, or it's just, I think my calculation, it is 80 or 8. You can help me with this. I'm trying to, that means this is simply 80. Okay. Yeah, that means this is 80. That means the average cost is like $80 per unit produced. I think it's 8. Okay, that means the average cost will be $80 per unit produced. Okay. But of course, I just wanted I wanted to show you how can you do this having a function. Yeah? Simply the same thing, calculating the total cost, dividing by number of units. Okay, now let's try to do another thing. Because I don't want you to be like not confident when you're reading a question. Because we know each mathematical question, when you see the solution, it's like trivial, right? Like, look at this one. It's so simple. But reading a question, yeah, we always have this moment, oh, like what function I have to apply, what formula I have to apply. That's the crucial moment. When I've been practicing, looking at the type of the question, the way that we ask, you will get your confidence, I hope. Okay, that's me now. Let's see this. If the cost in dollars to produce the units of a product is given by this function. That means, again, we do have a cost function. 2q cubed, excuse me, minus 60q squared plus 8,000q. What quantity will minimize the average cost? Okay, as we can see now it's like a nice application. We have to find a minimum value of the function. That's what we did in the first part of chapter 4. Yeah? Simply we have to have a function and we have to minimize. But what function? The average cost function. That means first of all, the same thing, the total cost divided by quantity. That means let's create an average cost function to, what I can actually do just to say, I will factor out q because q is a common factor for the function. And I will have 2q squared minus 60q plus 8,000. I mean, I will write this way, q, and then 2q squared minus 60q plus 8,000. And divide by q, because I'm following the average cost function. And dividing by q, of course, nicely we can see I can cancel out. That means my average cost function looks like quadratic function. 2q squared minus 60q plus 8,000. Of course, the coefficients are not friendly. That's when we have to find. But since this function is the quadratic function, we know that the graph of the quadratic function with the leading coefficient being positive, it's simply like the parabola open up. Right? That's we're looking at this point. We're looking at the vertex because that will be the minimum. The minimum we can see, that's the minimum, the local or even the global minimum value. Yeah, but we have to find, we have few different ways. We can use calculus, and we will use the calculus. That means in order to find a critical point, we have to find the derivative, and derivative is 4q minus 60. Okay, and then for the critical points, derivative is 0 if 4q minus 60 is 0. Then solving for q, 60 divided by 4, I think it's 30 divided by 2, 15. Okay, that's we do have q15. That's when critical point for the average cost occurs at q15, but we still don't know. We can try to use the first derivative test. But actually we know, because I just show you the parabola, that if I will put 15, I can test my derivative, and substituting let's say huge number to this formula, I will get definitely positive. And substituting 0 minus 60 will be negative. And this means that function is decreasing and increasing. We definitely have local minimum value. And of course, that's the shape of the function. Yeah, it's a quadratic function. Okay. That means this is definitely minimum value. That means when q is 15, average costs are minimized. And we can say when q is 15, I can say this, average cost are minimized. I think my spelling is correct. Okay, but we can see the way to work. Always, yes, find a derivative, because this function must be minimized. Okay? Again, I will use the blue color. You see what I did, right? I did create the average cost function. Yes, you're gonna be an expert with the average cost. Okay, good. Let's see what else I have. Oh, another question. The cost function is given. Okay, question. Yes, I can try to answer. Charlene, you have a question in this slide. Please ask. We can wait. You can all ask me the question. The answer boxed in. Okay, when quantity, yes, when q is 15, right? That's when q is 15, the average costs are minimized. When q is 15, average cost function is minimized. Oh, okay, yes, no, it was, okay, it was A. I didn't, because this is the average. Yeah, I know the writing, it's average cost function. Okay, that means I wanted to use the shortcut, but okay, Q and A, I know I write a little bit, and especially the electronic pen. Capital, okay, now it's clear. Okay, no, good. You want to know everything, right? You don't want to miss any question this week. Okay, next one. The cost function is given, C at Q is 1000 plus 20Q. Wow, so easy comparing to the previous questions. Find the marginal cost to produce the 200th unit and the average cost of producing 200 units. Okay, that's when we have to find the marginal cost and the average cost. Okay, and what we have, the cost function, it's nice and simple, 1000 plus 20Q, okay, just the linear function. And we remember that the marginal cost, it's simply a derivative of the cost function, which actually, if I take derivative of this function, 1000 will give me 0, 20Q is just 20. Okay? That means the marginal cost to produce 200 unit, the 200th unit is $20 per unit. Okay? That means this means is the marginal cost is, how can I write, is just $20 per unit. Okay? Because it's the rate of change. And the average, that's the marginal, okay? That's the marginal, find the marginal cost. That's the marginal cost. Now, the average cost of producing 200 units, of course, we know the formula. It's still the same. C, the total cost, divided by number of, why I am putting T, I really should put Q. Okay. I mean, this one will be cost for 200 units divided by 200. We went through this one. 1000 plus 20 times 200. We don't need calculator for this. 1000 plus 2 times 2 is 4 and 3 zeros. 1000 and 4000. It's 5,000. We can cancel out zeros. 50 divided by 2 is $25. That's when we do have $25 per unit. Okay? That's the average cost. Okay, that we have 20, the marginal cost is $20 per unit. The average cost is $25 per unit. Okay. Again, what we did, this one. What was the marginal cost? Marginal cost. Okay, remember what it is. Okay, that means that's, if you will be confident with these problems, you can check your section 4. Am I crazy? 4.5. Okay, now what I will skip this one. We do have a section 4.6. That means in section 4.6, we talk about the elasticity. As we have to know, I know, looks a lot, but you can definitely pause that video, that slide, and you can pause the video and you can read all of this information. But let's just go through some important one. That you will see this notation. Yes, delta P means that this is the change in price P of a product. Delta Q means that it's the corresponding change in the quantity Q. Dividing delta P over P is the percentage change in price, and respectively delta Q over Q is the percentage change in the quantity demanded. And then we can find, like delta Q over delta P, which for the small changes is simply the derivative, dq over dp, the rate of change of the quantity function with respect to price. Yeah? dq dp, the small changes in p. And then we have to know this, the elasticity of demand of a product will be labeled by E, and it's given approximately by the formula delta Q over Q, which is the percentage change in the quantity over the percentage change in price. Yeah, that means percentage change in the quantity over the percentage change in price. We can still try to rewrite this equation. Okay? I can divide price over quantity times derivative of the quantity function, okay, with respect to price. And then we do have some, we can do this formula, but that's important. If the elasticity is less than 1, demand is inelastic and revenue is increased by the raising the price. If the elasticity is greater than 1, demand is elastic and revenue is increased by lowering the price, of course. And if it's exactly 1, then we will have critical points of the revenue function. Okay, that's we do have some elastic, inelastic terminology. And let's see, that's some example. We can skip this. Okay, and let's solve the problem. That's what we have. Raising the price of a hotel room from $75 to $80 per night reduces weekly sales from 100 rooms to 90 rooms. Yeah, makes sense. If we put the price up, yeah, we didn't sell as much rooms as we maybe wish. Approximate the elasticity of demand of rooms at the price 75. Should the owner raise the price? Okay. Okay, that's first of all what we need. We need elasticity, but we will need a percentage change in price. Okay, that means we will have delta P over P. Okay, that's make sure that we know from that slide is percentage change in price, and how the price change. The price change from the price is $5 difference, right? But I can write 80 minus 75, and what is the percentage change with respect to the price 75? That means 5 divided by 75. This will be the percentage change in price. And I did use the calculator. I know that I can simplify, but it's 0.07, 6.7%. Okay, that means $5 is 6.7% of $75. Okay, makes sense. It means the price was the percentage change in price. Now the percentage change in demand, the quantity, actually what's happened from 90, from 100 we got 90. That means we decreased by 10. I can write this right away. Comparing to the 100 that it was. That means this is negative 0.1, negative 10%. Yeah, 10 rooms down. We are 10 rooms down. Okay, that we do have percentage change in price, percentage change in demand. Now, the elasticity of demand, EE, elasticity of demand. Okay, maybe I can do this way. And now what we have? We have to take dQ over Q, the percentage change in demand and the percentage change in price. Of course, everything positive. That we have 0.1 over 0.067. And as you can see what I'm doing, and using the calculator, this is actually 1.5. Okay, that means the elasticity is 1.5, one message, we're getting that this elasticity is greater than 1. That means it's definitely elastic and revenue is increased by lowering the price. Okay? It's definitely, it's greater than 1 because the percentage change in demand is greater than percentage change in price. Okay, that's 10 and that's, okay, that means now we do have the elasticity of demand, 1.5. We know what this means. And this was part A. Now the question is if the owner should really raise the price. That means what's happened? If the price was $75 per room, the revenue, can you tell me what is the revenue? Because I'm not asking you a question, I don't know why. The revenue was simply, because how many, 75, and he was selling 100 rooms. That means what was the revenue of selling 100 rooms of $75 per week? Of course, 100 rooms times $75, right? 75 and 2 zeros, $7,500 per week. That means this is his revenue without changing anything. Now, if he did 80, he changed the price. Okay, who can tell me that number? Then actually was 90 rooms, and price was 80. That means 9 times 8, we all know, 72 and 2 zeros. That means we can see $7,200 per week. That's his revenue. Okay? That means he increased, right? He increased the price, but he lost the revenue. That means the price should not be raised, right? We can see this. He should keep the lower price. That's the reason that they always have this sales in the store or some offers, right, for lower price, because then they will be more busy. Yeah? And of course it's worth it. And that means I was just trying to show you the idea, what this number means, That's the elasticity and some applications. Okay, now let's see another one. Okay, yeah, another question. The elasticity of a good is half. E is equal to 0.5, half. Yes, the elasticity is always yes. Oh yes, we're always positive. Yeah, absolute value means always positive, correct, right? Mm-hmm. Because it's just the indicator. Yeah, how elastic the whole sale is. Mm-hmm. Yeah, it's always positive. Okay, that we have the elasticity of good is half. What is the effect of the quantity demanded of 3% price decrease? Okay, what is the effect? That means what we have to do, the price decrease. That means decreasing by 3%. Probably I have to use negative. I will decrease by the 3%. Okay, that means what the effect of the quantity. That means what we have to what is the effect on the quantity demanded? Quantity demanded, which this means changes the percentage change in the quantity demanded. That we have to compute this, and this will be probably the percent. What is the effect on the quantity demanded? That means what I will do, I will start with because I know the elasticity. Yeah, it's always approximately. I can use this, or I can use the exact, because even in the formula we're using this symbol. That means what it is. This is dq over q delta p over p. And the percentage change in the quantity over the percentage change in price. But what we have, the percentage change in the quantity demanded, is negative product of elasticity. Okay, that we have to put negative. Okay, and then actually I will multiply both sides by negative delta P over P, and delta Q over Q will stay. Okay, I'm just using this equation and trying to solve for delta Q over Q. Now I'm just rewriting the sides. Okay, so now we do have half for the elasticity of the good, and the percentage change in price, because this is the percentage change in price, okay, it's simply negative 0.03. It's the 3%, which actually I can put the 3% for you. Okay, that means that's what we have to do. We have to just multiply. Mathematically, I wanted to show you, but we have to simply, in order to, since this is the elasticity is the ratio of the percentage change in Q and in P, then we have to just multiply the elasticity times the percentage change in the price. And this will give me, I can maybe write here, 0.5 times 3 will be 15, but 0.015. And this is 1.5%. That means this is my quantity demanded. The percentage change in the quantity demanded is 1.5%. But again, we're using this formula, because I'm not trying to like explain exactly mathematically, but we know that's the formula, and we just follow this. Okay? Make sure that you know the formula, and you can solve for dq, dp, just multiplying these two together. Okay, that means if the change in price is negative, as it is here, then the change in the quantity is actually positive. We can see this. So the quantity demanded increases by 1.5%. Okay. That's good. Let's see another question. Again, please do not try to miss any question. Okay, we have to understand, and we have to know how to approach. Okay, that means this one will be probably similar, but we do have. Let's see the scenario. Suppose the demand equation for a product is defined as a Q equals to square root of 100 minus 3P. Okay, where Q is the quantity demanded and P is the price in dollars. Okay, calculate the price elasticity of demand when P is 25. Okay, the same thing. We can start, we have to price elasticity. I can just box this. We have to know this. Delta Q over Q, delta P over P. But I will change this because we know that we can rearrange. And however, always, always negative, because then we're taking the absolute value. That means we can say this is let me do this one for you. P dividing by fraction means multiplying by the reciprocal, and then I can combine P and Q. That means I will have the ratio price over quantity, and I will have delta Q over delta P. Now I think this is better form of the elasticity equation for this question. Okay. Okay, that's what we need. And everything, okay, everything P is 25. That's what we will need. P is 25. and I will substitute 25. I need the Q, the quantity, when P is 25. That means 100 minus 3 times 25, because I need everything at 25. That means this is 100 minus 75, okay? Square root of 25, Q is 5. So we do have the price 25, quantity 5. Excellent. 25 over 5. Really nice. But now, delta Q over delta P, it's simply, we remember, it's simply the derivative. Right? That means having a function Q defined as a square root of 100 minus 3P, we can compute dq over dp. That's the same thing on the small interval, delta q, delta p. That means, remember, this is just the derivative. Okay, this will be the derivative of the q function of the quantity demanded function. Okay, and now hopefully we remember how can you compute the derivative of 100 minus 3p taken to the power of half, because square root means half in the exponent. I will use the chain rule. That means half in front times the quantity, the same, and take this quantity will be taken to the power of negative half, because I have to subtract 1 from 1/2, and times derivative of the inner function, which derivative of the inner function is negative 3. I use the chain rule. Yes, we remember, even if we're doing some application, we still have to know how to find the derivative of this function. Half the whole quantity to the power of negative half times negative 3. I can actually copy this. 1/2 100 minus 3 times p to the negative half times negative 3. Okay, and that's the quantity that we have to compute. Of course, p is 25. That's, we will substitute 25. Right. Let's try. This is 5. That's half. 100 minus 75, because I'm substituting 25 for p, to the negative half, and actually times negative 3. Maybe I can put that negative 3 here. Okay, I can. Negative times negative is positive, 15 over 2, and 100 minus 75 is 25. 15 over 2. Negative half means that we have square root in the denominator, right? Because half, the exponent half means the square root. Negative means that we have to move everything to the denominator. Okay, that's, we do have 15. Square root of 25 is 5, times 2 is 10. 15 over 10, oh, actually it's 1.5. We can say this. 1.5. That means demand is elastic, and revenue, of course, increases by lowering the price because it's greater than 1. 1.5 or 3/2 depends what we have, but we can see 1.5. Okay, that's my elasticity of demand, the price elasticity. Again, make sure that we can see this is maybe a little bit longer question, because we have to know the formula. I did rearrange, and the derivative. I'm just a little bit worried that maybe we don't remember, but try to make sure that you know how to compute this particular derivative. Okay? Okay. What else? Yeah, I have the question. You probably saw similar question on the first attempt. If you, of course, if you didn't take it, that's fine. But if you're gonna take the first attempt of the quiz, you will see similar question. Okay? And of course, the second attempt will also follow with this. Okay, let's keep moving. I will skip this. Let's try this one, because again, I'm just playing with the formula, or I'm trying to ask you different things, but playing with the elasticity of demand formula. Let's see what we have. Suppose the demand equation for the product of Suppose the demand equation for a product is defined by Q equals to 200 minus 4P, where Q is the quantity demanded and P is the price. At what price the elasticity of demand is just equal to 1. Demand unitary is just 1. That means the same thing. I will start always, yes, we have to do this formula, and I can maybe copy that form, dp derivative of the Q with respect to the price. Okay, that we need to find the value of P when E is 1. Okay. Let's mean what we need. We will need P. Okay, I will put the Q function in the denominator, and again this is just the derivative. Okay, derivative of the Q, which is now we have really easy derivative. Derivative of this function is just -4. Okay, -4. Actually, and we have to solve this equation for P. Let's try if we can make it. Negative times negative will be positive. 4 times P is 4P, and 200 minus 4P. Let's cross multiply. Okay, let's add 4P to both sides. Okay, that means P is simply 200 divided by 8, 100 divided by 4, 25. That means we have the quantity at what price the elasticity is 1? At $25. We can see we have to understand the components of the formula and go from there. That means you can see, do not miss that elasticity equation. Okay, let's keep working. I know I'm not asking much question, but I hope you're still there. I know, I can see good attendance. Okay, now we're jumping to the next section. 4 point, I believe is 4.7. That means for 4.7 we have to be confident with the logistic function. That means the logistic function looks like that. Probably we will provide for you, but let's see some characteristics. That means the carrying capacity and the point of diminishing. Okay, that means this function, if we will go through like the graphic, like calculator or some programming, that's the shape of this function. Okay, and yeah, we can see one thing I wanted to say. Okay, let me read. The function is defined as a L over 1 plus C times e to the power of negative kt. Okay. Now, this function, of course, that's the shape. This function, because the only information that is important, if this is the L, that's the L. But if we will take, I just want to tell you the maximum, right? What we have. I just wanted to tell you that the logistic growth curve is the fastest, right? When we have the half of the carrying capacity. That's what I'm just trying to explain this. But maybe we can look at the question. That means when the whole value is half, right? If this function will be equal to half of that number L, this means that we have the logistic growth curve is at the fastest rate. Okay? That means if we would like to see the fastest rate of growing, P must be half of L. Right? That's one thing. Okay, let's see what I have. That's what actually I'm trying to ask. find a point where the following curve is the steepest, which means the steepest means the fastest growth. Okay, that means the logistic growth curve has the fastest rate if this value is half of L, and L, actually this is L, right? That means that's what I use the word steepest, but of course means the fastest growth. That means if this is half, okay, of L, then we can try to find the point of time. So let's see if we can do it. Of course, L is 50, that means this must be 25. Okay, 6 e to the negative 2. I can divide this equation by actually 25. I will get 1 and 2. 6 e to the negative 2. I can cross multiply. This will be 6 e to the negative 2 and 2. I can subtract 1. I can divide by 6. And I can take the natural log of both sides. Okay, I did run. Let's take ln of both sides. And we know that this, having the natural log, will travel in front. That we will have negative 2t times ln of e and ln of 1 over 6. Ln of e, of course, is 1. That we do have negative 2t ln of 1/6. That means t, negative t, is equal to, I can divide by half, I can divide by 2, both sides. The negative, I can actually move the negative on this side, but I can also apply this negative here, because it's the same idea. I can take this negative and make it exponent negative 1. 1/6 to the negative 1 is just 6. Oh, I did run out of the room. That means the final answer will be 1/2 ln 1/6 to the power of negative 1. We have to just flip it. Okay, that means this is 1/2 natural log of 6. I did use the calculator. Of course, on the final test, this will be the good answer, but I used the calculator and I got 0.9. That means the curve is the steepest at the point where t is 0.9. Okay, that's what I wanted to. Let me come back for a second. Yeah, the steepest position, which means the point of diminishing returns is the inflection point where p is growing the fastest. Yeah, that means p is growing the fastest, and this happens when p is half of the L value. That means just remember this, half. Please know where the 25 come from. It's half of that L value. Okay? Then it's everything, it's like at the fastest rate. I was trying to explain this. Okay, and of course the exponential equation. You can probably get this. That means that's how we can solve. The most important thing on this slide is to know this equation and of course to know how to solve it. 25. That's for me the new concept. Okay, let's try what I have. That means that's the function, and that's the one of the main question from this section. I will skip this one because we do have the solution. That we can see this is actually the easiest way to ask you. The number of animals, n of t, has the following growth pattern. That means that's the growing function, where t is time in days. How many animals were there at the time 0? that we can simply take this function and substitute 0. I did type for you. 0, this will be 0, 1, and we can get the value. Yeah, that's, of course, it's nice and easy. The question that I just solved in the previous slide was a little bit more complicated. But having a function and substituting. Oh, Charlene is asking, it looks like the steepest is there, it's at yes, always the most steepest function is at L, yes, L divided by 2, always. Hang on, we can even, the 2, yeah, we can we can look at this function, yes, we can see the steepest function will be always at L, at half of the L, right? That means that's always the case. And the point where the concavity changes, of course, but that's the steepest function. Okay, and then I have another question. Oh yeah, that's actually the same thing. Okay, it's exactly the same thing. We the number of animals, n, has the following growth pattern. That means it's growing this way, okay? Where t, of course, is in the time. And at what time t, the second derivative is 0. That means we don't even have to approximate to the nearest day. We don't even have to think to find the second derivative and then put like the equation equals to 0 and solve it. We know that this is giving me for this function an inflection point. Inflection point, and this is the steepest position. That we know that this must be half of this. Okay, that means that's how we can deal, and then we can follow it, and it's exactly the same steps solving the exponential equation, solving for t. But please remember, this quantity came because of the inflection point, the steepest, L over 2. Yeah, the same idea. Don't think because I had one student was trying to solve because we can try to find the second derivative, say equals to 0, and we will get the same answer, but that's too much. We have to know the concept. Okay, that's the reason that we may also ask this way for you to understand mathematically. Yeah, just simply L over 2 is giving me the maximum, the steepest point, the inflection point. Okay, and then we have the last section. Yeah. It's also like another function, the search function, which is defined as a times t times e to the power of negative bt for the positive constants a and b, increase rapidly and then decrease towards 0 with a maximum, yes, with the maximum value being a t. Yeah, this is the maximum, being a t equals to 1 over b, 1 over that coefficient. Yeah, that's another way to look at this quite fast if we know. Yeah? And this is, of course, the amount, let's say the amount of if we take some medicine, that means we do have the peak of the concentration, and then, of course, the amount of the medicine is decreasing, but we do have that peak. Yes, the time of the peak of the concentration. It's always the reciprocal of the coefficient b. And that means that's another function that we can look at them quite fast. I mean, let's see. Oh no, I didn't want you to see the solutions. I wanted to solve it for you. But okay, let's see. Suppose that concentration of a substance in the bloodstream is modeled by the search function. Excellent, we do have a function. C at t equals to 60 times t times e to the negative 1/3 t. All right, that we can see the quantity b is 1/3. That's what I wanted to point. Right? B is 1/3. Okay. where the time t is in minutes, since the substance is consumed and the concentration in milligrams per liter. At what time does the concentration reach the maximum? That means even not looking at this my calculus solution, do you think you can tell me right away? That's supposed to be my question. Like, what is the maximum? I mean, what is the time that the concentration reach maximum? Do you remember from that? It's just the reciprocal of this coefficient. Okay, B. We have to take the reciprocal. That means if B is 1/3, what will be the maximum? It's simply 3. Okay, and we have minutes at 3 minutes. I'm just taking the reciprocal, 1/B. Flip the number 1/3, you get 3. And we can see we can still go through the calculus. In order to maximize the function, I need to find the derivative. That means you can follow my product rule. And then I have to solve this derivative for t if derivative is 0. That means solving this equation, we know that e to the power of any number is never 0. That means only 60 minus 20t will give me the solution. And of course, t is 3. And then we can do the test. And this is definitely maximum, because if I will perform the first derivative test, substituting, for example, 0, we will get positive, and substituting huge number, I'm getting negative. Increasing, decreasing, it's definitely maximum. But we can see how fast, knowing the property of the concentration of this function, we can get the number 3. Okay? That means you can always use our beautiful calculus way. Okay? But you can also remember the property. This coefficient, can you see that blue notation? You don't worry for the negative, just this. You have to flip this number, and this will give you the time that the concentration of the medicine or the substance reach the maximum. Okay? The same like I was trying to explain with the highest capacity of the other function, of the logistic function. Okay, and let's see what else I have. No, okay, that's now what we have. The same function. Suppose that the concentration of the substance in the bloodstream is modeled by a search function. We can see the same function where t is the minute since the substance is consumed and the concentration is milligrams per liter. At what rate is the concentration changing after 9 minutes? Okay, that means now we're asking at what rate? At what rate the concentration is changing after 9 minutes. That means what we have to do, since it's the rate, we have to compute the rate of change at one point. That's we have to compute the derivative at 9. And we do have derivative. We can see. You can try to, again, pause the video and follow the product rule, the same like the previous slide. And having a derivative, we're simply substituting instead of t, 9. Okay. That means this will be the rate of change, the instantaneous rate of change at 9 minutes, exactly at 9. Because the rate of change at one point, it's simply the derivative. That means we have the application, but we still focus on the math. That means the concentration is decreasing, okay, at the rate 6.03 milligrams per liter per minute. Okay? Because we do have, actually this should be negative. Because we can see if you will use the calculator, you will get negative number. That's the reason that I am saying decreasing, because it's negative. I mean, this was negative, this should be also negative. Okay, and I think, okay, I have one more question. Yeah, I shouldn't, but let's see what the question asks. The same function, okay, we know what, yes, we have the time, we have the function, and now calculate the maximum concentration to the nearest milligram per liter. Okay, maximum concentration. That's mean what we know. We know that the maximum concentration is happening at the time t. I can write this formula 1 over b, which of course is 3 minutes, at 3 minutes. This is of course b. I'm just repeating this. Okay, that's b, 3 minutes. And we simply have to take a function, I mean the concentration function, and substitute 3. 60 times 3 e to the power of 1/3 times 3. That's which I did here, and using a calculator, we're getting 66.42. Probably on the final test, this will be the final answer, 180 times e to the power of -1, and we can just leave it. But since we can use the calculator for this test, we can have the value. Right? But on this slide, we can see when we're asking for the maximum concentration, we really need the value of the function c at the maximum time, which of course is 3. We know right away. Okay, that's everything for today. I went through all of this section. Oh, no, I do have one question actually. Because from the discussion board, that's end of all of my questions that I prepared. And I believe when you understand every single question, every single concept, you will ace it, your test this week, okay? And then I think, okay, I did copy a question from the discussion board, right? Somebody asked the question on the discussion board. But what I realized, this one, of course, we have to know kind of like the shape of the function, but this is definitely a good question to practice, the question for the homework, for the practicing. It's not a good question for the test, because we do have some parts that really require like solving really complicated exponential equation. Okay, that we can try to get the approximation values from the graph. But let's solve it. Since this was asked and I did promise that I will solve it, let's just try to solve it. This question. And just this one, okay? That's what we have. If time t in hours and the concentration c in nanograms, probably, per milliliter of the drug concentration curve, for the drug is given by, and of course we do have nice function, right? We can see. I can maybe copy this function, 12.4 times t e to the power of 0.2 t. That means, can you tell me what is the b quantity? I can write here. What's the b quantity? Looking at this formula. Because the highest, we know the graph, of course, we have to use the computer to get this graph, but we know approximately the shape. And the peak will happen, okay, can you tell me the b value? I hope you're still there. I know that the session is, the b value is just this, it's 0.2. Can you see this? This is the 0.2. Okay, that means 0.2 I can write as a 2 over 10, which is 1 over 5. And the reciprocal of this will give me the maximum time. That means this is 5. The peak is at 5 hours, actually. It's not minutes. Yeah, that's what I want you to look at this search function, that recognize the quantity, the coefficient b. 1 over 5, the reciprocal will give me the maximum peak. Okay, that's when we kind of look at the function, graph the curve. Of course, we will not ask you to graph exactly. I mean, you can try to remember the shape like this, right? Is the peak concentration and then it's decreasing, and you know how to find this vertex, this top. Yeah? Like I just found it. Okay, now the question is asking, how many hours does it take for the drug to reach, its peak concentration? Yes. What is the concentration at that time? Or maybe we can answer this. We can see we have the answer. And that means this is actually the B part. It's giving me the maximum time, 5 hours. Okay. And if it's asking for the maximum concentration, then I have to take my C function and substitute 5. 12.4 times 5 times e to the power of 0.2 times 5. And I did use the calculator. It's 22.8 nanograms per milliliter. That's what I'm assuming. Okay, but we can see what this means. We did question like that. We took the maximum time and substitute to the function to get the maximum concentration. Okay, that means this is part A, graph, part B. What is part C? If the minimum effective concentration is 10 nanograms per milliliter, during what time period is the drug effective? Okay, that we just have to find if the concentration is 10 nanograms per milliliter, which is this 10, okay, then I will write a horizontal line because this is my time. Let's say T sub 1 and T sub 2. That we have to know the time because they asking during what time period. That means we can just say, that's what I said, in order to solve this one, this will be complicated to solve this equation. This equation equals to 10. Yeah, and then we will probably find, because we will find two values, T sub 1, T sub 2. But I'm kind of guessing, maybe you can help me. Maybe this is 1, and this looks like between 15. Okay, that means time must be between 1 hour and 15 hours. Yes, for the concentration to be 10 nanograms per milliliter. That's what I was saying, because algebraically will be not easy to solve. I'm just really using the graph and approximating. Okay, and now what is the question? Complications can arise whenever the level of the drug is above 4, okay, 4 nanograms per milliliter. How long must the patient wait before being safe from complications? Okay, that means that's like another thing. I mean, similar to part C. C of T is 4. That means 4 is somewhere here. And I have to approximate that because, of course, we're not looking at this. This is just growing, but this one, okay, that means after how many hours, like the amount, the concentration will be lower. I would say 21. That means after 21 hours, yes, it is safe to take maybe another dose. Yeah? After 21 hours, the patient will be safe, yes, from the complication. The answer is 21. But you can see, again, I'm not solving. What I'm saying, the function C is 12.4 times t e to the negative 0.2 t equals to 4. That's what I'm saying. We have to solve. I mean, it is not easy equation because we do have t and we have t in the exponent. That means it is quite challenging to solve this algebraically. But again, I'm just using the graph. And we will probably not ask you, we will give you easier function and easier question, just what I solved before this one. But in order to understand this question, you can see everything what I did is based on that graph. Okay, I hope that's clears a little bit the uncertain things about this question. Okay, thank you again. I will finish the session now. Oh, thank you for joining me.